Uh, Very good. Welcome back. In the first half of this lecture, we were talking about um, the information metric, the Fisher-Rao information metric, and how you derive that from uh, distinguishability. So let me comment a little bit more on what's going on there. Uh, the idea is we come up with a measure of the extent to which you can distinguish two probability distributions. To do that, you define this delta, which is just the relative difference between the two. And you can approximate by doing a Taylor expansion into this funny formula that involves the derivative of the law. And then you sum over the theta a's. As a first try to use this as a measure of distinguishability doesn't work because when you take these many numbers and you transform them into a single one by doing an average, you get zero. So that doesn't work as a measure of anything. But if you were to take the variance, just take this, the average of the square, then this turns out to be positive. It's greater or equal to zero, and it's equal to zero when these two are exactly the same, when delta vanishes. So this has all the properties you may want to have from a metric. So really this is an important realization. So what we're going to be doing next is going to say, look, normally when you have 2 points together close by, you say, oh, I cannot distinguish them because they're so close together, right? If they're a little bit blurred, like I look at them without my glasses, I cannot distinguish them. I cannot distinguish them because they're too close. What we're doing here is inverting that intuition and going in exactly the opposite direction. We cannot distinguish them, therefore they must be close. We are inventing a notion of distance associated to the notion of distinguishability. So we're saying something like this. By definition, we are defining distance so as to have the properties of distinguishability. This is a major move. So let me make another comment about possible implications. One of the important implications is, of course, that once you have a notion of distances, you have notions of volumes and all sorts of things, right? But I would claim that there is also, and you can do that for inference. You can invent uniform distributions and you can do all sorts of things. But there is another thing that may be more directly relevant for someone who's doing physics as opposed to just merely doing inference, which is the following. Uh, what's sort of like really interesting about having the concept of beta in statistical mechanics is that offers a statistical interpretation, a statistical understanding of temperature, right? This object is purely inferential. It's a Lagrange multiplier, and that allows you to get an understanding of what temperature might be. Um, Similarly, when we have the information metric in statistical mechanics, this gives you a statistical understanding of the thermodynamic entropy of Clausius, right? You understand things deeper when you do the statistical mechanics approach. So now this is the big question. When we say something like this, can this give us a statistical understanding of distance? And by distance, I mean not just the distance on the statistical manifolds. Now I mean we have a physics concept temperature, we understand it better. We have a physics concept, thermodynamic entropy, we understand it better. Could we possibly use this sort of idea to understand physical distance in space, right? Here, the space that we're talking about, the space. Can this tool, this new tool we have, namely that we have a statistical concept of geometry, of distance, can that help us build a better theory of physical space and therefore physical space-time at some point? That's a question that has not been answered yet because there is only one way to possibly answer it, which is, well, go ahead, construct a theory, make it work. In the case of statistical mechanics understanding of temperature, you make it work by saying what we're talking is about a system described by microstates, which may be points in a phase space, and we're going to assign a probability distribution on that phase space on the basis of having a prior measure that says a priori equal volumes are equally likely. And then we're going to say, oh, for equilibrium, then we're going to use this kind of constraint on the expected energy. You have to fill in all the details. But this opens up the possibility that we might actually know what we're talking about when we say we seek a statistical understanding of space. As I said, this has not yet been done. Einstein once said, or he used to say at least, that the reason we do not understand space and time is because space and time are the concepts that we use to speak about everything else. We do not have any way to speak about space. Space is what we use to think about other things. I would claim that maybe this offers us a possibility of having an understanding of space that is not directed to space itself, but rather to something else. Just a thought. This is, by the way, one of the reasons why I myself became very, very interested in all of these topics. Once you understand temperature better, once you understand entropy better, and once you understand that there may be a hint as to how to understand space better, it became very clear that this was an interesting thing to study. Very good. So, having discussed how we understand distance in terms of distinguishability, I would say that there is, well, this is a very nice approach because it's sort of like intuitive, relative distance, relative differences and things like that. You take averages. It's fairly intuitive, or at least intuitively after you've thought long enough that you think you understand it. There is a problem with this, which is that it's a little bit ad hoc. Why this particular measure of distinguishability? Why not other ones? Are there other ones? So that's the question. Are there other possible metric tensors? So let me write out what was the result of all of this was that the distance is given by a metric tensor, and then you do Pythagoras. This is just Pythagoras in the space of probability distributions in a curve space, right? Where G is this average, the derivative of the log, the derivative of the log. Again, it is a pretty ugly formula, isn't it? It's pretty awful. Then you learn to love it because it has so many nice properties. In any case, so we have this formula here that gives us a statistical understanding of the notion of distance on these statistical manifolds. What was the problem? Are there other measures of distance? Are there other ways to formulate a metric geometry on statistical manifolds? So while this derivation is very nice in that it provides a nice intuition of what it is that we're doing when we do information geometry, uh, it is very, very deficient in that it gives absolutely no hint as to where there are other possibilities. Is this just an arbitrary? Once you look at that formula, you say, this is awful. This can't be true. I mean, this is... Well, it turns out that this formula is essentially unique. This is the only way you can do it. And so this derivation is flawed or is imperfect in that it does not provide any hints as to why this is the unique formula for the metric tensor. So what we're going to do is we're going to derive this metric tensor from a different direction, which also will give you some intuition about how this actually behaves. But it's going to be to derive it from embedding in a Euclidean space. So this is a different approach to deriving the same formula. It also involves assumptions, but we will see how it works. It's actually very intuitive. Suppose that you have a space of discrete probabilities. So suppose that you have a simplex. Uh, the simplest is simplex. Let's write our simplex here. This is the space of all probability distributions. This is a probability distributions. The probability can be P1, Pm, such that the sums of the p's add up to 1, m, and the p's are all positive. We could set them also equal to 0, but it's a little bit easier this way. So this object, this space is called the simplex, and if we were to write it for the three-sided die, P1, P2, P3, this space in which the probabilities are normalized to 1 is going to look like a plane like so, where here the probabilities here are P1, this is equal to 1. On the plane P2, P3, P1 is equal to 0. So on that line, P1 is equal to 0. Here P3 is equal to 1. On the bottom plane, P3 equal to 0, and so on. This is the one here. So this is the space of probabilities when you have three alternatives, three values, 1, 2, 3. Oh, okay. So what we are going to do is we have no metric here yet. We do not know what metric to assign here. It does give you the impression that this is like a plane because I've drawn it in this funny way here. But that is actually not quite right. What I'm going to do next is I'm going to change coordinates. And instead of the coordinates P, I'm going to use the coordinates C, I, which are equal to the square root of Pi, the square root coordinates. With these coordinates, the normalization looks as follows. Pi, I1 to m. It looks like P Ci squared I equals 1 to m. And all of this is equal to 1. So this is sort of interesting. If the space P1, P2, P3 were Euclidean, flat, then this equation, the sum of pi is equal to 1, is really truly a plane. But if it is the space of the x's that is flat, then, so this is C1, C2, C3, then as you can see, come on, it doesn't want to move back. There, forced it. When you look at this equation here, you have the sum of the squares adding up to 1. So in the z coordinates, the simplex actually looks like the surface of a sphere like that, where that is the North Pole. So it's an octant, orthant. There are, if you were to complete the sphere, there are 4 in the upper hemisphere, 4 in the lower one. So this is an orthant, whatever awful word somebody invent that. We shouldn't use it now. But this is for the three-sided die, right? But it's spherically symmetric. So this is the trick. That's why this ends up being important. Well, actually, it ends up being important because assuming that the space of the P's is flat, Euclidean, that doesn't give you the right answer. However, if I assume that the space of X's is flat and Euclidean, so this is the surface of a sphere. This would be a 2D sphere, a two-dimensional sphere. The M simplex becomes an M-dimensional sphere. That actually is the correct answer. So in the space of X's, the geometry is that of a sphere. So we take this seriously, we declare it that it is a sphere, and we proceed to draw conclusions. So the idea then is going to be the distance, the metric tensor is going to be the xi, the xj. It's just Pythagoras theorem. Please notice I have not proved this. I have derived this from the assumption that the space xi1, xi2, xi3 is flat and Euclidean. I made the assumption. Once I make the assumption, this is the assumption. Okay, so I'm not proving anything. I'm just telling you different features of this information metric. In the case, for the particular case of these probabilities on the simplex. So how do I know that this is actually what we were been talking about? Well, if I were to remember what C was, C is the square root of the P's. Then the dxc, because I want to substitute back and find out what the probability, what the metric looks like in terms of the P coordinates. So if I just compute this from here, what I get is 1/2 P to the minus 1/2, 1/2 P to the 1/2, and then dP. And this is what I'm going to substitute back into dl10 dl squared is going to be the delta ij. There is going to be a 1/2 from the first factor and another half from the second half factor. So there is a 1/4. Then there is dpi dpj. And then there is a pi 1/2 pj 1/2. So pi 1/2 pj 1/2 1/2. But now the metric here is telling you, and this is summed over I and j, right? What this delta is telling you is that I has to be equal to j. So when I is equal to j, you get a sum over the i's of dpi squared, I equals j, and I sum over all the i's, and this I equals to that j, and so here we have pi, like so. This is one of those instances where you have to be very careful what you mean by metric tensors, that you're summing over I and j's, because this here, this I that appears here is being summed. Yes, and that's why I had to put it explicitly there, because here you have three i's, right? And that's, so the Einstein convention doesn't work very well here. You have to actually write it out explicitly. Very good. So the metric tensor in these coordinates is going to be uh, 4 pi, and then there is something that a Kronecker delta that tells you that you only have terms on the diagonal. So there you have it. That's the metric on a simplex. Now, of course, if you look at this expression we had up here, you say, what's going on? This looks completely different. Actually, it's not. Let me go back to the following and say the following. Suppose that in this simplex, here you have the space. This is a large simplex. So this is a simplex in m minus 1 dimensions. M for the number of axes, minus 1 for normalization. So this, and let me assume that this is a very large space now. So what I would like to be able to do in this large space, and maybe I should draw my picture differently. Here is the large space. There, you can see that it has many dimensions. What I would like to be able to do within this large space is consider a submanifold, and the submanifold here, we're going to write it as some parameters. Let me see, how do I write this? Yes, I'm going to say that this submanifold is given by the coordinates c that we had before, but expressed in terms of the parameters theta, uh, like that. So there is an equation here that says for every value of these thetas, I select a point in this submanifold. If you do that, then the change in one of these x's is going to be given by the derivative of xi with respect to the thetas, and now here you multiply by the d theta a. And the metric, the distance, is going to be given by, well, we had an expression for this distance, the sum of the dx's, dxj. So we had a formula, here it is, for what that distance was. It was the distance in the Euclidean space, right? So now we're going to substitute here, and we have the xij, the C d theta A d theta A and dCj d theta B d theta B. And so now once again we have here some kind of metric tensor. And if we go back now to our probabilities, you see when we have the connection between x's and the probabilities, the dx is going to be dp over p1 half with a factor of 2. So now I'm going to replace this by the pi the theta A, and there is going to be I should put it like delta ij. Here I have the dp, and then there is a 1/2 square root of p. So this is going to be 1/2 square root of p. So that's the first piece. The second piece is another 1/2 square root of p j dpj d what d theta b d theta a d theta b. And now we see we have a 1/2 1/2. We have a 1/4. Then we have the Kronecker that makes me sum over I and sum over j, but the i's have to be the same. So this is going to be a sum. The i's have to be equal to the j's, right? The sum over 1 over square root of pi, 1 over square root of pi, 1 over pi, v pi, d theta a, v pi, d theta b, and then d theta a, d theta b. We're almost there. You can see here that you have the derivative of p divided by p. This is the derivative of the log. 1/4 I derivative of the log of p d theta a. And that takes care of the first two terms, the two factors. Then we have the p d theta. So let me divide by p and multiply by p. I multiply by p here, and I divide over there. When I divide, I get another log. And then, of course, theta A, theta B. So when you look at this factor in front, you see that this is the discrete version of exactly this formula we had before. Instead of integrating over x, we are adding over I. So it's exactly the same thing. So when you try to figure out the metric by making this assumption uh, of distinguishability, you get one result. When you actually assume that the space of x's is spherically symmetric, is flat, then you get basically the same metric. It's just the variables x are different here, right? There is an idea. So this is how you can start seeing how the geometry here is always coming back to the same sort of metric tensor. Let me derive the metric from yet another um, path, which is actually sort of connected, much more directly connected to statistics. So this is going to be a derivation from entropy. The idea is going to be something like this. Imagine that you have your famous statistical manifold and you have a probability distribution there. When you do any sort of maximum entropy calculation, you're going to rank all probability distributions relative to the probability distribution that you have there. This is the probability distribution that is parameterized as the point theta. So here we have coordinates theta 1. Here we have coordinates theta 2, and you can put as many axes as you want, right? And I'm ranking these guys according to relative entropy, relative to the point theta. So what I would like to know is, remember, this is differential geometry. So while it is true that I can assign an entropy really far away from the point theta, what I really want to know is, can I distinguish a point theta from a point that's really near to it? How high ranked is a point that's near? Consider the entropy of the probability distribution theta plus d theta. I'm running out of space here. Theta plus d theta relative to the point that of course is ranked the maximum, right? This is, if you maximize subject to nothing, the point that's ranked the maximum is going to be that this guy coincides there. So now I'm going to say, if I go a little bit out, what happens? What is this number? Well, remember how we even derive this formula. We derive this formula by imposing that prior information is very valuable. You want to be as close as possible to the prior, right? So if it is as close as possible to the prior, can we actually say that this is a distance? And the point I want to make is that yes, you can, provided you are sufficiently close, because distances in curved spaces only work when you are sufficiently close. Otherwise, you have to add over many individual segments along a curve. Here we don't have curves or anything, so this is only individually very sufficiently close. Very good. So let me do this. And how do we proceed? We would like to say this, whatever this entropy here is, let's call it, this is the entropy. Yes, let me rewrite this formula here. It's even better. Let me write this entropy here as the entropy of a theta prime, theta prime, uh, relative to theta when theta prime is equal to, well, just a small change. And so now if I am going to write this small change, I'm going to write the entropy of the distribution theta plus theta prime, this one, relative to the distribution theta. And what I'm going to do is I'm going to Taylor expand, because I want to be very close, right? And so when I Taylor expand, the first term is the entropy of theta relative to theta, the probability of the entropy of px theta relative to px theta. And you can see what that's going to be, right? Because if you have px theta divided by px theta, that's going to be 1. The log of 1 is 0. So the first term vanishes. Then you have the second term. The second term is going to be that one. Now, when you have the second term, what happens? Well, this one here is equal to 0. Entropy was concocted, there is that minus sign in front, so that the maximum, in the absence of no new information, you do not update. In the absence of no information, the probability that the distribution that maximizes this entropy is when theta prime equals theta. So if you compute what the maximum is, the point theta is going to be the maximum. The first derivative vanishes because S theta prime theta is maximum at theta prime equals theta. Very good. So if we try to do this expansion, the first term vanishes, the second term vanishes, the first non-vanishing term is going to be the next term in the expansion. There's going to be a minus sign. Oh no, well, not yet. Not yet. The minus sign is part of entropy, but this is the piece that has the second derivative. The theta prime b evaluated at theta prime equals theta, and then you have the theta a d theta b. So this is the first non-vanishing term, and if you look at this entropy and you look at this expression here, you immediately see that this is, whatever this is, it has two indices, AD, summed over two indices, AD. This starts looking like a metric tensor. Because this is a maximum, the second derivative is negative. So we're going to propose that S, the second derivative of S, d theta A, d theta, actually, let me write it better, that S theta plus d theta, comma, theta, this is going to be a distance with a minus sign. And just for the normalization, like previously we had in the previous one, we had an extra factor of 1/4 floating around there. Everything else was the same, but you had that overall constant. Here we're going to have an overall constant as well. Oh yes, which I forgot to write here. If you're going to do the Taylor expansion, this terms comes with a 1/2. So this is going to be the 1/2. In fact, what is that term? Delta L squared. If we compute now the second derivative, d theta prime b, let us add theta prime equals theta. Let us compute that. And let me put, I'll put the minus sign here because entropy has a minus sign, so that will cancel the minus sign. And so this is going to be the following. Second derivative, theta A, theta B of the integral of, and what is, we're taking derivatives of the entropy. So there is a minus sign that cancels, and then there is the P x theta prime log px theta prime divided by px theta. So this is the quantity we have to evaluate. We have to take two derivatives of the entropy. Let us take one derivative first and then the other. So here we go. The derivative theta prime A of this guy here. Very good. When we take the derivative with respect to theta prime b of this guy, we're going to get the log. Here we go. The log we take the derivative, and then we multiply by the derivative of this guy here. Derivative of px theta prime d theta prime b. So now with this move, we have computed the derivative of the first piece. Now we have to compute the derivative of the second piece. Okay, let us separate the log into two pieces. Log p theta prime minus log p theta. The derivative of the log p theta prime with respect to theta prime b is going to be, it's a derivative of a log. So it's 1 over p that cancels this guy, and then the derivative of p, which is out here. So it's going to be plus 1. The derivative of the second piece, log px theta, is 0 because I'm taking derivatives with respect to theta prime. So this piece here does not contribute. So this is it. We've taken the first derivative successfully. Now let's take the second derivative. When we do the second derivative, what we're going to get is there is the derivative of the log p theta prime, which is going to be 1p x theta prime, derivative of px theta prime divided by theta prime b. That's the derivative of this piece. The derivative of the log px theta is 0 because this is theta prime. There is no theta prime there. So this is the derivative of this guy. The derivative of 1 is 0. So then we have just this other piece here. Plus this whole term, let me write it all by itself. Plus 1. And now we take the derivative of the last term over here. So this is going to be d2 px theta prime d theta a d theta b. And we're done. Now we can simplify all of this. Then there is, let me write the dx there. Very good, we're done. When you look at the last term, this is going to be evaluated at theta prime equals theta. When you do that, this is equal to 0 because you get the log of 1. Then you have plus 1 and you get this second derivative. But now notice that if you take these second derivatives, the integration is over x. So when you take the second derivatives here outside of the integral, when you take the second derivatives outside of the integral, this is, the integral is normalization, it's 1, take derivatives, going to be 0. So this term here goes to 0 as well. And what we are left with is dp over p, which is the log, divide by p, multiply by p, you get a log again. So the conclusion is that the derivative with respect to the first argument, second derivative with a minus sign, evaluated at the max is equal to the x p derivative of log p theta derivative log p d theta, which is exactly what we had before. So from entropy, you also get exactly the same sort of metric tensor. Whenever you have a metric, whenever you have an entropy and you are considering what happens in the vicinity of the maximum, that tensor uh, is actually the metric tensor. Maybe it's time to stop here. We have gotten the metric from three different directions, uh, three different, very different approaches, and we always keep getting the same metric. This might seem like an indication that perhaps there is something fundamentally unique there, something universal going on there, and that is indeed the case. Next class, we'll discuss a little bit more how it is that the proof of uniqueness goes. This is the unique metric for statistical manifolds. So it's really an important uh, concept. Whenever you have something that's universal, you have to pay attention. This is one of them. See you next time.